let's watch this. So I'm going to press record. All right, so going back to share screen. All right, since I just started the recording, reminders would be the quiz will be on, depending on the block schedule for next week. To reiterate again, since I just started the recording now, for the second period, your quiz will be on Monday, 8 to 10. For fourth period, it'll be on Monday, 10:15 to 12:15. For third period, it'll be on Tuesday from 10:15 to 12:15. And then fifth period, it will be on Tuesday as well, 12:45 to 2:45. So please make sure that you log in during those times, because that's when your quiz will be available. And after that, it'll be taken down and you won't be able to get access to it. All right. On this first slide, this is a PowerPoint that was shared, and there are new slides added to it, so make sure to look over the new set of PowerPoint. The key for this particular one is the whole concept that intermolecular force is really what determines the change in phase. Solid is denser, so they have more intermolecular forces, but when you give them enough energy, aren't they able to kind of break apart from each other, creating something that's more liquid, or in fact, if we give them too much energy, then they can go into the vapor phase, or they turn into gas. We also read a quick article about glaciers melting. So for last night, I started going through all their responses, and I'll try to input that by today. I have like one more period to get through, but this was one of the individual things that I needed you to respond to. So just reminding you, questions could come out of that article as well. All right. Last week, we also described some of the properties of liquids. The three main ones that we talked about was viscosity, volatility, and vapor pressure. And the way to remember viscosity would be if you compare water with a honey or ketchup, whichever one is more sticky or the one it flows slowly, then it's more viscous. So it is related to the intermolecular force. The stronger the attraction of the molecules, the more viscous that material is. So they're directly related. The second and the third one are also connected to each other. A way to visualize this, what we use as an example would be gasoline. So if you spill gasoline, they tend to evaporate quickly, meaning they're very volatile. So volatility is the ability to evaporate. And the way to connect that to vapor pressure is if they evaporate quickly, then that means there's more gas that's being formed, so there's greater vapor pressure. So key points, volatility is directly related to vapor pressure. The more volatile something is, the more gas is being formed. So they're higher vapor pressure. There were other properties last week that we addressed. The example we used for this was water. Water has high surface tension because it has hydrogen bonds. Pause, there's a question in our chat. I probably will have to, let me see if I can view that. It looks like I'm going to pause the sharing. So the question is, what's the definition of vapor pressure? I guess the best way to define it would be the amount of gas produced by a phase change. So at least in the context of what we're talking about in class. So if you have a container, the more of the gas that's being formed in there, then there's greater vapor pressure. So it's just really a measure of the amount of gas in a particular container. So it's the answer, Kelly, to your question. All right, so going back to our list here. Sorry. I paused the screen share, so let me go back to it. All right, so back to this. The other properties, capillary action, the greater the intermolecular force, the more that we can observe that ability of a substance to travel up a thin kind of chamber, or in this case, like imagine a straw. The thinner the straw, the higher that water line could go. the one on the right, boiling point, it explains why water has such high boiling point because it has strong intermolecular force. The stronger the intermolecular force, the more difficult it is for us to turn it from liquid to gas. So it has a higher boiling point. And then the last one is just an illustration that every liquid has its own density. So the picture shows that there's quite a few different liquids in there, and we can separate them based on their density. All right, this table, it was, depending on the period, you might have seen it, others didn't quite get to this. But what I'll do is I'll go through each one. So on the left side, we have 3 of our main types of intermolecular force. And then the second column are examples that goes with it. Remember that London dispersion is the weakest. So in terms of the third column says strength of attraction, then it would be considered the weakest intermolecular force or the lowest. And then because it's not strong, then doesn't it mean it's easy for us to break apart those intermolecular attraction? So if London dispersion is weak, I can separate the molecules easily, making them very volatile. And if it's turning into gas quicker, then can't we say it will produce more gas? Therefore, it has a high vapor pressure. So to repeat, the first row, London dispersion has low attraction or low strength, and then it's high volatility, which means high vapor pressure. So that's the answer to the first row. For the second row, isn't dipole are medium or middle in terms of the strength of intermolecular force? Because it's in the middle, then all across the board, the answer to that would be medium or middle. So dipole is medium in its strength. It is medium in terms of its volatility, and it's also kind of the midway point in terms of vapor pressure compared to the other two. Hydrogen bond, the third row, is the strongest. So we know it has the highest strength of attraction, and because it's more difficult for us to break them apart, then that means that it is low volatility. It doesn't evaporate quickly. And if there's low volatility, there's not a lot of gas being made. Therefore, it's also low vapor pressure. So that's the answer to this table. Then Friday, we had the chance to go through certain vocabulary here. And so take a look at the list. And then what I'm going to do is unmute the video so that way you guys get the chance to ask something. If questions come out of this, it'll really be based on, it'll be more of a definition type of question.
What is crystalline?
Think of salt. So salt, if you look at the structure, isn't it like, you can have like a big chunk of salt, but then if you kind of crush it, it breaks up into smaller and smaller cubes. It's a crystal structure. So visualize salt would be an example of a crystalline structure.
Thank you.
You're welcome. Let me unmute everyone else in case you just have to mute. Just the chat. Or maybe you can type your question. Any particular question in the vocab? All right, if not, we're gonna keep going. That gives us more time for the math portion. All right, so back to this. So again, it'll be mostly a vocabulary type of question. Thursday, you and your partner were working on a phase change POJO. And for that one of the key graphs that you were asked to try to analyze and try to explain was a heating curve. So what we're looking at is known as a heating curve. And you'll notice in terms of how it works, it's like a step-by-step. So for example, I start on letter A, solid, and let's use water as an example. It's easier to visualize. So we have solid ice. If I keep adding energy to that solid ice, then over time, I'm gonna get to the point where it'll reach the melting point. So the portion where A and B is kind of meeting up. So like, here's the top of A and then B. So at that very corner, that would be considered the melting point of ice. And every time there's a flat portion, there's a phase change happening. So in this case, if we're going from A to C, then isn't that a melting of ice? And then if we're going from, so that's the first flat portion. The second one, the one that's higher up between C and E, then that would be evaporation or vaporization. So the takeaway for this, the more energy we add to a compound, it will go through a change in temperature. So every time it's an incline, there's a change in temperature. But then every time there's a flat, there's a change in phase. So they're going through a change between solid, liquid, and gas. We could reverse the whole thing. And that's why one of the questions on your POJO was, how would you draw the cooling curve? And wouldn't it be just a mirror image of this whole thing? Meaning now it's starting high. So it'll go kind of like, I wish I had a diagram here or like a whiteboard to show you. But it's exactly a mirror image of this. Starting high and it just keeps going step by step until it reaches the solid phase. So it's questions can come out of a graph. It might say, here's the heating curve. Can you describe what's happening when it's on the flat area, or what's happening between part A and part C, something along that line. Another way that we can represent phase changes would be a flow chart that looks like this. So in this case, it's showing us the 6 main different phase changes that's occurring between the 3 main states of matter. Keep in mind there is plasma as well, but for what we're talking about right now, since the unit's called solid, liquid, and gas, we're not really addressing plasma. But just know the vocabulary terms. Some of the majority of this is familiar. There's a couple that might be kind of unusual or something you might not have heard from before, like deposition. I'm hoping sublimation is nothing new, something that you might have heard from before. There is a slide that we didn't quite get to last week, but it's something that we need to address. I might have mentioned it in class when we were talking about liquids. There are certain liquids that seems to kind of have their own special properties. So these are called the non-Newtonian liquids or non-Newtonian fluids. The examples we have here. So for the quiz, you'll see on this table, there's all these like rheopectic, thixotropic. Don't worry about those vocabulary terms. I'm just giving you an idea that there are different kinds of non-Newtonian liquids. The picture on the upper left is showing cornstarch with water, and it's called oobleck. Maybe some of you have played with oobleck before. And the thing with that, the texture of that non-Newtonian of oobleck is if you try to hit it with enough force, it acts like a solid. But if you just dip your finger in there slowly, it will actually act as a liquid. So depending on the force you're applying to it, it will change its property, or behavior. Another example, and you'll see on the right side, honey, cream, tomato sauce, and ketchup. They tend to display non-Newtonian fluid properties, where if, let's say for honey, if you let it sit there, a jar of it, and let it sit there for months, it'll solidify for the most part. But then you can liquefy it by either heating or by trying to stir it. And the more you stir it, the more liquid it becomes. So we're changing its property based on the amount of force or energy we're applying to it. So that's the takeaway for this slide. Non-Newtonian liquids are special because they display both solid and liquid properties. All right, the next few slides are what I talked about 2 days ago. So, you know, that I've kind of spent some time on. So I'd rather spend time on the math portion of it. So if you were able to get through this whole thing, make sure that, people were asking me about this slide, by the way, since there's like multiple formulas. For Boyle's law, the formula that we really need is the one that says P1 V1 is equal to P2 V2. The one above it, the PV is equal to K, is the actual definition of Boyle's law. But in terms of the math that we're going to be doing for the Boyle's law, it's really the one that's P1 V1 is equal to P2 V2. Same thing with Charles and Avogadro's law. The formula we're using are the ones that has um, the initial and final, like the ones and twos. So that's what the 1 and 2 signifies, like condition right now versus the condition after something changes. So just keep in mind that that's what we're going to be doing. For the next slide here, what I'll do, let's see. So let me show you this, and again, this is available for you. But one thing that, or the usual issue that students encounter is when they see the word problem, they're not entirely sure which formulas to use, especially since when the quiz on Monday, you'll have, you can have your formulas written down in front of you, but it's choosing the right one that will solve that problem. So I'll go through each one and I'll kind of walk you through like how I would approach it if this was one of the quiz questions. First one says, I have 10 liter of a balloon. So that's giving me volume, one of the first numbers. It's telling me that there are 3 moles of gas. So I have volume and moles. So 2 information that's given so far. It started to leak. So it's telling me that there's a change that happened to this balloon. And now it's giving me a new volume of 5 liters. They're asking for moles of gas. So they gave me 2 volumes, 10 and 5. There was a change in volume, and they gave me the moles of gas. With that in mind, this is looking like it's an Avogadro's law calculation because I have volume and moles of gas, initial, and then they're giving me the volume final. What's missing is N2. So with that, it involves you having to rearrange your calculation to solve for N2. Now, number 2 says a container is a mixture of different gases. We know the individual pressure of each gas. How can we solve for the total pressure? This particular question is not one of the 3 in the previous slide. It's not Charles, Avogadro, or Boyle's. It's if you had looked at the PowerPoint from Tuesday or Wednesday, further down there was a topic called Dalton's partial pressure. And what I'll do, I'll show you how to solve Dalton's partial pressure. For this one, there are no numbers, but I'm just letting you know that this type of question is a Dalton's partial pressure question. There is a chat question. So Ella is asking if it gave you both the amounts in grams, you need to do the mole conversion. Yeah, I'm assuming, Ella, you're asking about a Dalton's partial pressure question. If so, the answer is yes. The grams has to be converted to moles. Oh, I see. It could be, you might be asking the question about the previous one, number 1. Then yes, you do have to change all the masses to moles before you can use Avogadro's law. And in fact, all of the formulas that has moles in it, like if the problem is giving us grams, we have to divide by the molar mass to turn it into moles. So on Monday, I highly recommend to have a periodic table printed out, or like on your computer, a tab that's open, so you can always go back to the molar mass, like the periodic table, to find the molar mass of that compound. All right, let's take a look at number 3. So they're saying you have a plastic container that has 10 liters. So our first data is volume, and it's at 25 degrees Celsius. Our second data is temperature. It was heated, so they're saying there's a change that occurred. What will happen to the volume of the container? It looks like there's a third number I can't quite see right now, but there's a third number in this data point. So they're letting us know that we are given volume and temperature, and there's a change in temperature, but they're asking for a new volume. This is pointing at Charles' law. V1 over T1 is equal to V2 over T2. And what's missing is V2. It says what will happen to the volume of the container. Charles' law, so if you're taking notes, keep in mind that the temperature has to be in Kelvin. So that 25 degrees is given in this problem, and then whatever that change is, it looks like, let me see if I can view the number and show you guys, 80 degrees. So those 2 temperatures have to be converted to Kelvin. It has something to do with the fact that some temperatures could be negative. Like if it's really cold outside, it could be negative 10 degrees. And if you just plug in degrees Celsius in Charles' law, you're going to get negative volumes, which doesn't work. You can't have a negative volume, then it doesn't exist. So the way to go about Charles law calculation is it has to be converted to Kelvin. That way your answer, the volume that you're solving for, is correct. So keep that in mind. Charles law has to be in Kelvin. The volume could be in liters or milliliters, but it depends on what the given in the problem. So, and I'm not going to try to trick you on that. Like for Charles law, the one thing really is the temperature. Temperature has to be in Kelvin. All right, number 4. A scuba diver needs to know how many moles. Before we keep going, there's a question. For pressure, do you want it to be in ATM or kilopascal? One of you said, oh, it has to be kilopascal. Right, so it depends on the question. And what I mean by that, let me close this. Okay, I'm gonna go, I'll answer your question by using number 5. So for number 5, they're telling us that they have this artificial lung where there is an initial volume of 0.5 and a new volume of whatever it might be. I think it's like 3 liters. Double check. It's, yeah, 3 liters. So they went from initial volume, final volume, and they're giving us the pressure of 1.5 atmosphere. If that number was in like kilopascal or torr, it actually doesn't matter for this question. So this is a Boyle's law question because it's pressure and volume. So that's what they're giving us for number 5. Part of the reason why it doesn't matter for pressure is the units will cancel each other out. So in essence, it's it doesn't matter if you have to convert it for or you don't have to do a conversion unless the problem states like what if the given is 1.5 atmosphere and then they're saying what is the pressure in torr, T-O-R-R, then that requires a conversion. For Boyle's law, all the other ones like Boyle's, Charles, and Avogadro, we're going to give you a bit more like straightforward questions. Except again, Charles you have to convert the temperature. It's the one that requires conversion typically is question 4. So again, for question 5, you, just kind of check the question. Is it asking you to convert the pressure to something else? And if not, then keep it based on what's given in that problem. So for question 5, if you solved it, your answer would be in atmosphere, which is fine because the problem is not asking you to do an extra conversion. Now, question 4 is something we've seen, or it's based on the formula we've used in the past. And it was the gas stoichiometry, the ideal gas law. Remember that formula is called PV is equal to nRT. So it's that Pevnert formula that I mentioned in class about 2 or 3 weeks ago. And I'm going to write all the formulas in one slide, but the key for this is that if you're given the problem where it requires a PV-nRT calculation, they're very limited, like meaning they will say the volume has to be in liters, the pressure has to be in atmosphere, N is moles, so it has to be in moles, and then T has to be in Kelvin. So PV-nRT, and let me show you the slide that kind of reminds you all of that. It's this one right here. So we've seen this same exact slide from a few weeks back, and it's also posted in the updated version. If you printed the PowerPoint from 2 days ago, that doesn't include solids and liquids, so you might want to print out the newer version. But for PV-nRT, we do have to remember that pressure has to be in ATM, volume in liters, N is in moles, and T is in Kelvin. The constant R is, the R we're using is this one, the 0.08206. So, since it's, in a way it's an open notes type of quiz, you can always refer back to this PowerPoint or maybe have something written down, you can go back to it. We're not going to be using the 8.314. That one is for next unit for thermochemistry. But for right now, we're using our R constant is 0.08206. All right, let's try some practice problems. Maybe some of you have printed it out, but I have on the slides that are provided, I'm going to use some, like this particular slide right here. We're going to try some of the practice problems. But I have to, the problem is that I can't write on the screen. I can write on like a blank screen that they provide on Zoom. So I'm gonna, again, if you have this kind of available, maybe have it like in a separate tab and kind of like go back and forth. But what I'll do right now is switch to our whiteboard. All right. So to do a quick review, the formulas you'll need for the math portion of the quiz next week. There are 5 of them in total. The first 3 are the ones that's on this PowerPoint from 2 days ago. So the first one is Boyle's Law. So that would be P1, V1, P2, P2. Again, for this, the units of pressure and volume, it depends on what the problem is giving you. So you might not have to convert. Typically, the pressure is in atmosphere, and typically the volume is in liters. The second one on our list, I'll put this in the box, was Charles' law, V1 over T1. It's hard to draw with here, V2 over T2. All right. This is the one you do have to remember something. Temperature has to be in Kelvin. So that's something that we have to keep in mind. The third is, it looks almost exactly the same, V1 over N1 over V2 over N2. For this, it's called Avogadro's law. And I think this is one of those problems where, what if they get, you were provided mass, then you do have to calculate the number of moles by dividing with the molar mass. So these were the main 3 from like the discussion 2 or 3 days ago. Now, there is the PV and RT, the ideal gas law. So let me write it here, PV and RT. And remember that this is the one that's very restrictive, meaning there might be certain conversions that has to happen before you could use it. The pressure has to be in atmosphere, the volume has to be in liters, N is moles. R is a fixed number that you can use and refer back in your notes. And then temperature has to be in Kelvin. So this one usually will require you to do some conversion. And we'll look at a practice problem that's related to that. The last one is Dalton's partial pressure, where it basically says the total pressure in a container is equal to the pressure of one type of gas plus the pressure of another type of gas plus, and then there's usually like a ellipsis kind of suggesting we could go on and on depending on how many gas there are in that particular container. So I'll help you with the study guide question. Remember there was one, the task from yesterday. I'll help you solve that one when we get the chance. All right. So what I'm going to do is one of the slides has practice problems for Charles, Boyles, and Avogadro, and I'll just pick one of them. So for example, let's start with question 2. It says we have a hot air balloon, and let me write like what's given and also what they're asking for. So question 2 says we have a hot air balloon with a final volume of 5,000. Question, what is the equation for the gas stoichiometry section in the study guide? For that, it was, so from when we were way back in gas, so I'll write it here, but I will eventually need the space. Remember that for gas stoichiometry, it was the mass given divided by the molar mass of the given. And then we need the mole ratio. So this would have been, I'll just put number of the unknown over the number given. Meaning you go back to the balance equation because it's a stoichiometry question. So when you, for that calculation, I think you were given a certain mass. You have to divide of propane, from what I recall, it was propane, and you had to divide it by the molar mass. Sorry, I was trying to highlight. You have to divide by the molar mass of propane, and then you have to look at, the first step for that problem was you needed to balance the equation. So what is the coefficient of the unknown? It was oxygen that they're looking for. And what's the coefficient of propane? By solving those first two steps, what you're solving for really is n. Because now, what do I do with that information? From what I recall, that question was asking what is the volume? Isn't, if I rearrange PV and RT, if I rearrange this and solve for volume, then doesn't it end up as nRT over pressure? So now in that problem, should have been given, or what's given in the problem is temperature and pressure. The R is a fixed number. The R again does not change, 0.08206. The N is what you solve for here. So by doing this series of steps from dividing with molar mass, multiply by the unknown coefficient, divide by the unknown, or sorry, by the coefficient of the given, you solve for N. That number you plug in here, and that will help you solve for the volume. All right, hopefully that answers that question. I do need to erase this step. So write it down and take a picture because I need the space to solve the previous problem we have here. All right, so I'll erase this real quick. Okay, going back to our given in this problem. So again, I'm looking at the second practice problem here. It says a hot air balloon is final volume of 5,500. They're telling me it's the final volume, that must be V2. So it says 5,500 liters. And they are telling me that that the final temperature, so T2, is 120 Celsius. They're saying, what if the initial volume, so V1, what if V1 is 3,200 liters? What must be? So what they're asking us to solve for is, it says, what is the initial temperature? What is T1? All right, so looking at this, it looks like we got to do a conversion first. I need to turn this 120 degrees to Kelvin. So isn't it 120 plus 273? 273. And I'm going to start. So that gives us with 393 Kelvin. 3 Kelvin. All right. Now let's put all the numbers in their appropriate spot. What I typically like to do is I want to rearrange my formulas first, my variables. Asking us to solve for T1. The problem is T1 is in the denominator. It's in the bottom portion here. So I need to rearrange everything so T1 will be by itself on the other side. So the best way to go about it would be, technically the shortcut would be called like cross multiplication, meaning like, I guess, let me write it. Some of you are like, yeah, I can do this, but it helps to kind of visualize how to best go about this. So it's a bit messy. All right. So the way I would go about this is I would move this T1 over here, move this T2 over there, meaning cross multiply them. And then finally, I need T1 by itself. So V2 will now be divided on both sides. So V2 will end up here. If rearrange, it should look like this. If rearrange correctly. T1 will now be V1 over V2, T2. It's a bit messy again. So if I do the rearrangement correctly, erasing this right now, our temperature initial would be equal to, it's going to be equal to the product of initial volume times final temperature over the final volume. So all I did again is a rearrangement of the variables, because once I've done that rearrangement correctly, then I could plug in all my numbers. So for example, to plug in all these numbers, our V1 is 3,200 liters. So that's 3,200 times T2. And based on our conversion here, T2 was 393. And then divided by V2, our V2 is given in the problem, 5,500. With that, so I could have this space here. It looks like our answer is 100 times 393. It looks like we have 228.6 something. And the unit for this is in Kelvin. In terms of the sig figs for next week, the problem with this setup is like 5,500 has 2 sig figs, 120 has 2, 3,200 is 2. So I'm kind of like limited by my sig figs. We'll try to make sure that the numbers you'll get next week will have enough significant figures so we don't have to round too much. And I'll consider, like, obviously it's harder setup for us right now because you can't show your work on the quiz. It's going to be just like writing your final answer. So there will be obviously some error, acceptable error that we're going to look into. But if you calculated that correctly, it should be 228.6 Kelvin, or if rounded correctly, it's really 230 Kelvin based on the rounding that needs to happen. All right, let me open this up and read all. Before I keep going with the math, any particular problem from either the study guide or from the PowerPoint you'd like me to address?
Could you possibly tell me the difference between a fusion and diffusion?
Okay, so they're almost, they sound the same. They're related to each other. But if fusion, an easy way to visualize that would be if you're using as a hairspray, or like you're using a air freshener. So how fast the gas is escaping through that tiny opening is the effusion rate. Now, once you sprayed that, let's say like all the air spray is you sprayed in one side of the classroom or one side of the bedroom, but then eventually, don't you smell it on like everywhere? It starts to diffuse. So it goes from the area where it's highly concentrated to an area where there's less concentration of it. So that would be an example of diffusion of gas. It's moving from where it's more concentrated to where it's less concentrated until everything kind of evens out so you can smell it in the entire room. So that would be an example of diffusion.
Thank you.
You're welcome. Any other concept or math?
I have a question. Could you do like an example for Dalton's law of partial pressure?
All right, so for that one, I'm going to use our study guide. So
Okay.
the one from yesterday, let me find the exact question. Because the thing with Dalton's law of partial pressure is you could get a pretty straightforward question. Okay, here it is. So let me, I do have to switch back to the screen so I can write things. Whiteboard, share, and I'm gonna clear all this. All right, so now the thing with Dalton's law of partial pressure, the main idea of it is pretty straightforward. And all it's saying is if you have a container with several gases, the total pressure is just a combination of all the individual gases. A simple question you might ask might be, what if they say you have nitrogen, you have oxygen, and what if the pressure of nitrogen is 1 atm, and then the pressure of oxygen is like 2 atm? Then all we really need to do, if you're asking what is the total pressure, is you add them together, right? So it could be as straightforward as that. Now, the other type of questions that could be asked would be in the unit of moles. So we're using the example that we have in their study guide. And there's something you have to, you have to remember about gases. The pressure, let me write it here. The pressure of the gas is, what does that weird symbol mean? Like it looks like a fish. What am I trying to say there?
Proportion.
Proportional.
Yeah, or directly related, right? The pressure of the gas is directly related to the number of moles. Or in essence, what I'm saying is, if I have a container and if one particular gas, there's a lot more of that gas, then aren't they contributing to the pressure? They're more of the main contributor to the total pressure. So the more moles of gas, the greater the pressure that they're contributing to it. So that's our main idea. But now, how does that work with the practice problem for the study guide? So for this study guide question, it was saying, what if we have a container that has 3 moles, so 3 moles of nitrogen, 2 moles of oxygen, so 2 moles, and they're saying we have 1 mole of CO2. So visualize that that's what we have. I should point out that temperature given is not part of the calculation at all. The reason why it was provided in the problem is that if we change the temperature, the pressure inside will change. So it has to be stated that 25 degrees is what's known as room temperature. So they're basically saying, when we do this calculation, we're assuming all of the gases in that container, they're all in the same temperature. So don't get kind of like confused by that temperature. It's not part of the calculation. All right, so now the way to approach this is, what's the total number of moles of gas? Like how many moles of gas do we have in this whole container? What's 3 plus 2 plus 1 is?
6.
6, all right, so we have 6 moles total. Just put total. So now what portion is nitrogen in this entire container?
1/2.
It's 1/2, right? And to show that, isn't it 3 moles for every 6? So there's 3 moles of nitrogen for the total of 6. What I'd like you to do, or there was something else, sorry, in the problem I forgot to mention. In this problem, they told us the container as a whole has a total pressure, P total, of 10 atmosphere. So that's kind of like what the, if you read that word problem in the study guide, they said, here's how many moles for each type, and the total pressure is 10 atmosphere. If half of the gas in there is nitrogen, can't we make a, using this idea that the pressure of the gas is directly proportional to how many moles of that gas, can't we say half of the pressure must be because of nitrogen? To prove that, you basically do calculation, 3/6 times 10 atmosphere, the total pressure, that gives us 5 atm of N2. So nitrogen is contributing 5 atmosphere in that entire container. Now let's try the rest for the other 2. Oxygen is 2/6 times the total pressure of 10. That gives us 3.33 repeating of oxygen. Because isn't oxygen contributing 1/3 of the pressure in that container, because it's 1/3 in terms of the number of moles of gas in that container. And then CO2 is 1/6 times 10, so that gives us 1.66 repeating of CO2. In total, when you add it up, I mean, it's not a perfect 10 atmosphere, you know, it's like 9.999 repeating, but the idea, if rounded, the individual pressure of nitrogen, individual pressure of oxygen, individual pressure of CO2 added together adds to the total pressure of the whole container. All right, question on that.
On the study guide, you said to like paraphrase the laws, but I had even the video that you put out on Canvas, I have no idea how to paraphrase Dalton's law of partial pressure or the gas stoichiometry one.
Oh yeah, the gas stoichiometry is kind of, it, in a way, it's like I'm saying, instead of writing the steps, how would you write it in words? That's kind of,
Oh, okay.
yeah. And even with this, like to write it in words, aren't we essentially just saying the individual pressure adds up to the total? That's kind of like what we're saying for that. All right. Any other specific one? We have about 7 minutes, so we have a little bit of time for any specific question, concept, or math. Let's see, what else I should point out to you guys? Yeah, since the quiz is a Google form, it's important that you work on the math calculation. Like it's best to have like a scratch paper, so that way, because the one concern is if you plug in all the numbers on the calculator, it's easy to kind of like, you know, things that need to be multiplied, you might end up like switching them, and then you end up with the wrong answer, because there's no, unlike when we do our in-class quiz where I look at your work, it's harder for us to do that now. It's now dependent on the final answer. So what if you had a good idea of how to solve it, but you messed up on the calculation, your final answer would be wrong. So that's gonna, you know, to be more careful, I would write everything down first, since time is, although it's, you know, it's a block schedule, but 2 hours is plenty of time to get the quiz accomplished. So I guess what I'm saying is you're not going to be rushed to like try to solve it. So you might want to double check your solution. All right. Anything else you'd like me to address, concept or?
Yeah, so what should we expect tomorrow on the test? Like, is it going to be like what our study guide looked like, or are we going to have like a definition kind of thing? Like
It'll be a mix, yeah. So there will be, because if you think about solids and liquids, all of those are conceptual. So they're vocabulary and concept-based type of questions that come out of it. For gases, it'll be mostly math-based type of question that I could ask. But it could be, in terms of the concept, I could say, imagine if you have a container, if I increase the temperature, what happens to pressure? So that would, you know, that's still a concept question. I'm not asking you to solve anything, but I'm asking you to predict what would happen based on the changing the condition that's given.
For the Dalton's partial pressure, when we're putting that in as our answer, would we put in like the 5 atm of N2? Like, would that be our answer?
Yeah, because for this one, let's see, it says calculate the partial pressure of each gas in the mixture. So on the study guide that's given to you guys, the answers would have been 5 atm, 3.33 for oxygen, and 1.66 for CO2.
Okay.
Anything
Mr.
else?
I have a question. So all the information on the gas topic PowerPoint that you posted before this one, is that all on this PowerPoint? Or
It is, yeah. All I did was I took that PowerPoint and I added the slides for solids and liquids.
Oh, okay, cool.
It was the same.
Are you going to be posting this recording on Google Classroom?
I am, yeah. So that's why earlier in the beginning, I wanted to make sure that I recorded this so I could share it with everyone.
All right, thank you.
You're welcome. All right, anything else? Okay. Send me an email for questions. And again, I'm going to have to update the Google form that I posted because I forgot that there's a switch in schedule. So the reminder again, you know, since people, maybe you didn't hear in the beginning, it doesn't hurt for us to reiterate that schedule for next week. The quiz will be posted for second period. It'll be posted on Monday from 8 to 10. For fourth period, it'll be on Monday from 10:15 to 12:15. And then if you're in third period, it'll be posted on Tuesday from 10:15 to 12:15. And then finally, fifth period, it'll be posted on Tuesday from 12:45 to 2:45. For all the class though, you have to check what's happening, because if, let's say, you're not doing the quiz Monday, that means, it doesn't mean you have nothing going on. It just means the schedule for the odd and even number classes are just going to be switched. So for some of you, for half the class, you'll be doing, or for half of my classes, they'll be working on something else, the next topic, but then their quiz is the next day. Or for the other half, their quiz is on Monday, but then on Tuesday they'll be working on the next. So check every single day for the announcements that I'm posting. All right, I think we could stop right here. Thank you everyone for showing up. Let me stop the sharing, and I'm gonna end the meeting. Bye everyone, stay healthy.
Thank you.
Yes.